This video is on heterogeneous equilibrium. We'll be following along with this note paper. It's a pretty short video, and in actuality, we have discussed a little bit of this, so this will just be kind of concreting this idea. So, of course, we have homogeneous and heterogeneous equilibrium, and so far, we've really only dealt with homogeneous equilibrium, which is when we have all substances in the same phase. So most of the time, the reactions that we've done have been like all aqueous reactants and products, or all gas reactants and products. And of course, if it's an all gas reaction, we know we can write a Kc or a Kp expression. So up until this point, we've been dealing only with homogeneous equilibrium, but now we know that there can be heterogeneous equilibrium, which means that substances are in different phases. And it really doesn't change a whole lot. It just changes the writing of the Kc expression. And so that's what we're going to talk about. Again, this should be a very short video. So the example, like kind of underneath that in that blank space is this reaction, which is an ionization reaction. And so you have a reversible ionization reaction. You have a solid ionizing into two aqueous substances. Obviously, this is a hetero equilibrium because we have a solid and then we have two aqueous substances. So not all substances are in the same phase, and therefore it's classified as a heterogeneous equilibrium. Okay, so, and we have mentioned this before, but it's been a little while. When we go to write a K expression, all solids and liquids are excluded from, from your equilibrium constant expression. So let me erase just a little bit so that I can squeeze this in there. So we have mentioned this probably back in our intro to equilibrium, or equilibrium constants, I guess. So in this case, if I was going to write a Kc expression for this, where I'm normally so used to doing reactants, products over reactants, and it's still that same thing, it would be the concentration of the Pb plus 2 times the concentration of Cl minus squared. But in this case, there's no denominator because the denominator would be the concentration of the solid, and we just learned that the solid is excluded from this equilibrium expression. So then thus this would be my Kc expression for this reaction. And the reason for that is that because solids and liquids pretty much have constant concentrations, meaning they're not really changing. And so if they're not really changing, then they're not represented in a Kc expression. And so there's kind of more to that story, but that's kind of the simple takeaway. So we could calculate a Kc value for this reaction if in fact you knew the concentration of the lead ion and the concentration of the chloride ion, and then you would just plug them in. Now, kind of an important point is that for this reaction to reach equilibrium, the PbCl2 solid must be there, okay? So I think sometimes that is the misconception, that if, in this case, the PbCl2 is not in the equilibrium expression, so maybe it doesn't have an effect on the equilibrium. And so that's kind of misinterpreted, because while the concentration of the solid doesn't have an effect on the Kc value because it's not in the expression, I have to have this. I have to have my reactant in order for equilibrium to be established. It's just that its concentration in and of itself does not affect the value of Kc. So that's just something to think about. So don't come up with the don't misinterpret that to mean that I don't need PbCl2 for this reaction to occur to reach equilibrium, because of course we do. But it's just that it's not in the expression for the equilibrium constant. So then you could have a reaction that looks like this. Which is actually a very interesting reaction, because if I were to write a Kc expression for this, so again, Kc, always product over reactants, well, I think about the fact that I have one product who's a solid and my only reactant who's a solid, which means I'm going to ignore them altogether. They're not going to go into this expression, which means the Kc for this reaction would only be the concentration of the CO2, which seems odd to us, okay, but that's what it would be. Or in this case, of course, because the one substance that would appear in my K expression is a gas, I could also write a Kp value, which would be the partial pressure of the CO2 at equilibrium. So actually, if you were to calculate the partial pressure of the carbon dioxide at the partial pressure of the carbon dioxide at equilibrium, what you in fact calculated is the Kp value, because the Kp is equal to the partial pressure. So that's kind of one of those odd situations where the equilibrium expression really reduces down to just one thing. And in this case, it's either equal to the partial pressure of the CO2 if it's Kp, or of course, if it's your Kc, it's the concentration of your CO2. So sometimes these expressions look very different if they're heterogeneous than if they're homogeneous, like we're used to working with. So at the bottom of your paper, there's just 2 practice questions, and then that's it for this idea of heterogeneous equilibrium. So if you want to write those expressions, I'll put them up, and then that's it. So the first one, I have 3 gases and 1 liquid, so they asked me to write a Kc, so products over reactants, and I'm going to ignore the liquid. So my product would be CO, and then over my reactant, CO2 times H2, and so that would be the Kc expression. Again, I've left out the water, and then B, so again, they're asking me to write a Kc. In this case, I have 2 solids, 1 product and 1 reactant, so I'm going to leave those both out from this reaction, so meaning my Kc is going to be equal to the concentration of my carbon dioxide gas squared over the concentration of my carbon monoxide gas squared, and that would be the Kc expression for this reaction. So takeaway point is just in writing a Kc expression, or a Kp expression, I guess, any solid or liquid in the reaction is removed from the expression. Basically, it's just ignored.